Alright guys, we're going to talk about scaling perimeter area and volume. So just a couple of things. Perimeter refers to lengths, right? Which is one dimension. Area refers to some two-dimensional space. So one dimension. Area is two dimensions like length and width. And volume is this three-dimensional concept of height included with base and length as well. So three dimensions. And that matters because it helps us to make sense of why we scale the way that we do and what a shortcut we could take is. So when the dimensions of an object are multiplied by x, the perimeter is multiplied by x because that's just the dimensions added up. The area, because it's two dimensions, the length and the width are going to both be multiplied by x. So in other words, that's x times x, or x squared. And the volume is multiplied by x cubed. I should write x times x times x, or x cubed, or x times x. And so we're remembering that each dimension is multiplied by that scale factor. And so if we wanted to do a direct shortcut to say, I know the volume of my scaled model of my tiny house in cubic inches, but I wanted to figure it out in feet, I could use my linear scale model and multiply by that 3 times, or times that cubed. So you can explain why that makes sense in terms of dimensions in your own words, but it does have to do with the fact that each dimension has to be multiplied by that scale factor. So for each dimension that you're working with, you need to multiply by the scale factor again. So that means that if you knew the scale factor, it's not necessary to know the area in order to find the ratio of the areas. It's not necessary to know the volume in order to find the ratio of the volumes, as long as you know what that scale factor is. So what's the scale factor from the small to the large ducky? If I want to go from 4 to 6, 4 times something equals 6. And I'm just going to use x as a reminder that this is times something. So if I wanted to solve for this, I'd divide both sides by 4 and find that x, my scale factor, equals 6/4. And when I simplify, that's 3 halves. So 4 times 3 halves, sorry, I shouldn't have used an x there. Should have used a dot. Times 3 halves equals 6. So the ratio of surface areas of the two similar duckies, now granted, I would not want to try to calculate the exact surface area of a rubber ducky because that's not an easy shape to calculate and they're irregular, and this is more where we need calculus to help us out. But we don't actually have to know calculus to think about the ratio of surface areas. So I know that if the singular dimensions are scaled by 3 halves, then to calculate the area, I just need to square that scale factor. And I don't have to know the exact surface area of either ducky to know that the ratio of the surface areas will be, the larger one will be 9/4 bigger than the smaller one. Or in other words, this is 2 1/4. So the larger duck will have a surface area that's 2.25 times bigger than the smaller ducky. So the larger duck will have a surface area 2.25 times bigger. What's the ratio of volumes? Again, we're just going to take that scale factor and cube it. So we multiply 3 halves times 3 halves times 3 halves. And when I multiply my fractions, 3 times 3 times 3 is 27. 2 times 2 times 2 is 8. And when I simplify that, I get 3 and 24, 3 and 3/8. So the larger duck has a volume that's 3 3/8 times bigger than the smaller duck. What percent change is there between the small and large ducks? or between their heights, their areas, and their volumes. Okay, so percent change is a nice practice for us. So what is 3/2 in percent? So the height is one dimension. So 3/2, when I want to think about percent change, this one's 1.5 times bigger as a decimal. 1.5 times bigger is equal to how many percents? Well, 1 represents 100%, and 0.5 represents 50%. So this is going to be 150% of the original. But remember, percent change doesn't include that original size. So it would actually be minus the original 100% to say that this larger duck is 50% taller. And when we think about that, that makes sense because 4 to 6 only grows 2, and 2 is just 50% of 4. So the percent change is how much it changed. If you wanted to convert this scale factor, 3/2, it's 1.5 times bigger, but we have to remove that original 100% to think about that change. All right, so the areas scale factor is 9/4. When we think about that as a decimal, we said it was 2.25 times bigger. That would be 225% of the size of the original, but I want to take away that 100% of the original to think about how much it changed. So it's 125% bigger area. And then the volume scale factor is 3 3/8, right? So 3 3/8 equals 3.375, and that equals 337.5%. But I want to take away that original 100% to think about the percent change. So it's 237.5% bigger volume in volume. Okay, so that is, in a nutshell, thinking through how the scale factor can help us to think about the ratios or the relationship of change between the area and the volume of different shapes. If we know a linear scale factor, we can use that to think about how the area relates from the original to the new, and how the volume of the original and the new shape might relate to one another. And then thinking about percent change is a nice bonus practice for us here to consider how language really matters, and that change really emphasizes the fact that we need to think about removing that original 100% in order to think about what's changed here. If it just said what percent of the original is the large to the small, then we would stick with these original figures. But thinking about percent change means we have to think about removing that. And this is a lot of thinking through what's the question asking. All right, thanks guys.